Hey, it's Mr. Doro. Today we're going to be talking about the ideal gas law. The ideal gas law is a very commonly used gas law, and the good news is you only need one pressure, volume, or temperature. And so this is the ideal gas law, PV equals nRT, where PV and T, you know what those are, but N is the number of moles, and R is a gas constant, which means it's going to be the same all the time. More about that later. Well, here's the ideal gas law again, PV equals nRT, and we can put them all together to make up this law. The most important thing on this page, though, is that you need to know that it doesn't work well at very, very low temperatures or very high pressures. And the reason why, at low temperatures, those gas molecules are going to start being attracted to each other and go back to a liquid, and the same with high pressures. More collisions, more attraction, and more possibility for them to become a liquid. Well, I said we'd talk about those values of R, the gas constant. It's called a universal gas constant, and there are 4 different values that I have listed here. The only difference between them is the units. The units are really, really weird on the gas constant. So if we look at this one, 0.08206, this is liter atmospheres per mole Kelvin. That's how you would say that. This is joules per mole Kelvin, which is the same as the Pascal meter cube per mole Kelvin. We really won't use that one. It's the same number right here. 8.314 liter kilopascals per mole Kelvin. And then if we had millimeters of mercury, the only difference here is the pressure each time. The pressure units keep changing, but if we're given the pressure in millimeters of mercury, it's going to be 62.4 liters millimeters of mercury per mole Kelvin, and that's all to cancel out all those other units that are on there. So you want to write those universal gas constants down. I want to talk about the volume of 1 mole of a gas under different conditions. 1 mole is 6.02 times 10 to the 23rd molecules. And so depending on if the volume can change, if the volume is variable, then that volume could be different under different conditions. If you have medium temperature and medium pressure, then you're looking at the size of the balloon right there. But if the temperature gets high, then you start to increase the volume of that balloon. And if the temperature gets low or the pressure gets high, it starts to decrease the volume of that balloon. So what we have is we have something called standard molar volume. Standard molar volume happens at STP, at standard temperature and pressure. No matter what gas you have, if you have 1 mole of a gas at standard temperature and pressure, 1 mole is going to occupy 22.4 liters. That is standard molar volume of a gas at standard temperature and pressure. That's very important because that helps us out later on. So let's get to the problems. Here's a problem, and it doesn't even tell you what type of gas it is. It doesn't matter. Ideal gases all act the same, and they act like ideal gases unless they're at very low temperatures and very high pressures. So we're going to label what we're given here. We're given the number of moles right here. That's N. We're given 1.96 atmospheres, which is a pressure. I don't need a 1 or a 2 because I'm only given 1 pressure. This is a temperature, and it wants to know what volume is it going to occupy. So we're going to do the ideal gas law, use the ideal gas law, PV equals nRT. And so we're going to plug in what we know, 1.96 atmospheres. We don't know V, that's what we're asked to find. N is the number of moles, 2.84 moles. And then I need R, that universal gas constant. So I'm going to pick the one that has atmospheres in it. The one that has atmospheres in it is 0.08206 liter atmospheres per mole Kelvin. Notice I didn't complain at all when I wrote that big old unit on there. Times the temperature, which is 323 K. Look what's going to happen to our units here. Atmospheres here are going to cancel out with that atmospheres. Moles over here, down here, are going to cancel out with the moles up there. Kelvin are going to cancel out with Kelvin, and we're left over with liters. So now I just got to solve for V. And when I solve for V, I plug this all in. I look at my sig figs. I need 3 sig figs, and this is going to be 38.4 liters. That's my volume using the ideal gas law. It works out really nice. Okay, so here's another problem. It gives me a pressure in kilopascals right there. I know that's my pressure. This is my volume. It tells me standard temperature. Standard temperature then is going to be 273 K. It'd be nice if this was at standard temperature and pressure, because then I could just do a quick action line to change that over, but it's not. And it wants me to find grams of oxygen gas. This one tells me it's oxygen gas. So I'm going to start out with my ideal gas law. I don't have grams in my ideal gas law, but I got something else that might be helpful. PV equals nRT. I have my pressure is 99.8 kPas, kilopascals, whoops, that's times 20.0 liters equals, I don't know N, that's my number of moles. When I find the number of moles, then I can change it to grams using a simple action line. But R is my universal gas constant. This one I need the one with kilopascals in it, which is 8.314 liter kPa per mole Kelvin, times my temperature, which is 273 Kelvin. And when I go through all this stuff, I need to get N all by itself. So really what I'm going to do is I'm going to multiply this times this, divided by this, divided by that. And when I do that, I end up with N equals 0.879 in 3 sig figs moles. And that's moles of oxygen. I know I didn't put that in scientific notation because that's really not my answer. I want to get to grams. And so then to get to grams, this is moles of oxygen. And so I have 0.879 moles of O2. I want to find out how many grams that is. This is going to be moles of O2. This is grams of O2. For every 1 mole, there are 32 because it's O2, 32.00. I need 3 sig figs for my answer, and I get 28.1 grams of O2 is what would occupy all those conditions. Now here are a couple problems for you to do. The first one's pretty straightforward. It's just a straight up ideal gas law problem. The second one, there's a little trick to it because it gives you grams. Grams are not moles, but you can change grams to moles, and then you can plug it in the ideal gas law. Now, it just says standard pressure, and I never told you which pressure to use. So really, you can use any gas constant you want, but then make sure you put the pressure in the correct units. All right, have a great day.